So in this talk, we're going to share with you some of our latest results on the thermo-mechanical effect of Wellbore cooldown and how it can impact the hydraulic fracture initiation from wells in high temperature formations. So just to give you some ideas of what exactly is Wellbore cooldown and why it is often necessary for geothermal wells and even for some wells in the hot unconventional reservoirs. So as we all know that drilling and stimulation in those wells oftentimes face challenges due to the high temperature nature. So here are some examples, the photos taken from the Utah Forge EGS site. These are the damages caused by a high temperature environment. So one of the common approaches to mitigate this potential damage and to increase the survivability of various devices and equipment involved in these operations is to actively cool the borehole through cold fluid circulation and for a period of time before lowering all these devices. And this method has been proven to be effective. And here again, I'm using an example of the Utah Forge. So prior to the mini frac tests at well 16B, cooling circulation was carried out for about 16 to 40 hours, and the measured temperature drop at the borehole is about 30 degrees Celsius. So this cooling circulation might seem to be a small and irrelevant step in the preparation for well stimulation, but it can actually have profound implications on the hydraulic fracture initiation that follows this process. So how does cooling circulation impact hydraulic fracture initiation? We find that cooling circulation facilitates the fracture initiation in mainly two ways. So first, we find that the cooling circulation can lower breakdown pressure. And here I'm kind of jumping to my conclusions. So the first finding is actually not new for some people. This is well documented in the past studies, and they all directly or indirectly indicate that the usage of cold fluid can effectively lower the pressure required for breaking the rock. And these studies are all focused on the thermo-mechanical effect of hydraulic fracturing as well as borehole breakout. And I list several studies here. And basically, this stress analysis provides an overview of the thermal effect. So this is for computing the breakdown pressure. And it is this term that's related to the temperature that's causing the breakdown pressure to drop. So if we are effectively inducing a cooling temperature of delta T, so negative for cooling, then we are lowering the breakdown pressure by this much. So our first finding that cooling lowers the breakdown pressure is consistent with all these previous studies. But we also find that this stress analysis cannot explain some of the observations we find in the field as well as in lab experiments that I will show later. That is the second major finding. That's cooling circulation can also change the geometry of the hydraulic fracture. And what we mean by that is if we take a look at this lab scale hydraulic fracture initiated from a borehole that's drilled along the minimum in situ stress direction. This is a complicated geometry in 3D, but if we are to ignore some of the minor fractures and simplify it into a 3D sketch as shown here, we find it's a mixture of two major types. The first is, as you can see here, there's a fracture plane that's parallel to the wellbore axis. So we will call this the longitudinal fracture. And the second is we see here's a big fracture plane that's perpendicular to the well axis, and we will refer to it as our transverse geometry. So as the fracture grows away from the wellbore, we would expect it to realign to grow in the more favorable direction, which is the transverse direction, because that's the normal to the minimum in situ stress. But in the near field, there's clearly this kind of competition going on between these two major geometries, the longitudinal and the transverse, and this is causing this tortuosity. And we would like to demonstrate in both numerical simulations and lab experiments that cooling circulation can change and can promote the hydraulic fracturing along the transverse direction that's perpendicular to the Wellbore axis direction. And this change in the geometry can only be captured by considering the full solid fluid interaction in the process of hydraulic fracturing in the presence of a significant thermally induced stress disturbance. So if you keep that in mind, I now introduce you the problem setup. So the entire problem consists of several steps. So the first step is cooling circulation. As you can see, as soon as the circulation starts, the temperature at the borehole drops relatively quickly from its original value, which is the wellbore temperature, the reservoir temperature, to the cooling temperature. And it remains more or less constant throughout the entire period. And after circulation stops, there's still some time before the hydraulic fracturing stimulation. And during this time, the temperature will slowly increase with time because the circulation has been terminated. And we'll call this the waiting time or the warm-up time. And finally, a fluid is injected into the borehole to create a hydraulic fracture at time 0. So this is our third stage, that's the hydraulic fracturing initiation and the propagation. So here I plot a typical evolution of the temperature at the borehole along with the injection rate and the wellbore pressure. So these two are for the third stage, the hydraulic fracturing. And we impose a constant injection rate. And this is the wellbore pressure evolution. It increases linearly almost with time at first, and then it reaches its peak value. This is the breakdown pressure that we define in this study. And then after that, it slowly decreases and converges to the normal compressive stress. So one thing to keep in mind here is that this x-axis, these values are not drawn to scale. That is because typically hydraulic fracturing is much quicker compared to the first two stages, the cooling and the circulation. And one extreme case is that if we are to reduce the warm-up time to be nearly 0, then we have our thermal effect maximized. So in this case, the temperature at the borehole remains at its lowest value, which is the cooling temperature. And we will investigate both scenarios with and without a warm-up. And because of the nature of this problem, we then can divide it into two subproblems. So the first subproblem is the cold fluid circulation and warm-up. So here we are combining these two stages, and we solve for the heat diffusion during this time and get its associated temperature field. And then for the second subproblem, it's the hydraulic fracture initiation and propagation. And we solve for the solid fluid coupled hydraulic fracturing and the injection of a constant flow rate. And so this time in the second subproblem, the hydraulic fracturing is much shorter compared to the first two stages. And this allows us to impose that the temperature is constant throughout this duration. And then we can just neglect the heat diffusion and solve these two problems sequentially. So we solve the first subproblem and get the temperature and then use it as the input in the second subproblem to find the corresponding fracture initiation and propagation. So here are more details of the numerical model. For the subproblem 1, we construct a finite element model in Abacus. So here's the geometry. And for all simulations, we will use the geometry of a horizontal well that's drilled along the minimum in situ stress direction. So once the circulation starts, the temperature is dropped from its original value to the cooling temperature. So we prescribe a constant temperature boundary condition at the borehole wall. from the beginning of the circulation. And since the initial temperature field is uniform, it's the reservoir temperature. So the heat will be slowly diffused into the rock. And after circulation stops, we then remove this constant temperature boundary condition to let the temperature increase with time. So this problem is symmetric with respect to both x and y axis. And that's why we reduce our geometry into a quarter of the original geometry. And this is the overall size. We have a 2.5 by 2.5 by 10 meter block. And z-axis is the borehole drilling direction. So we are effectively circulating a 10-meter borehole interval. And this is the mesh we use for solving this problem. Again, we are solving this part of the problem. And at the end, we get the corresponding temperature field and use it in the second subproblem. So this is the model for the hydraulic fracture initiation and propagation. So I remind you that we are now solving this part of the process. So the initiation and propagation of a hydraulic fracture is driven by the injection of Newtonian fluid with a constant injection rate into a linear impermeable rock. And our main goal is, again, to investigate the competition between the two geometries, the longitudinal and the transverse. So the longitudinal geometry is equivalent to a plane stream biwing hydraulic fracture emanating from a circular hole. So as you can see from this planar view. And the second geometry is the transverse. It's the same as a 1D axisymmetric hydraulic fracture growing from a wellbore here. So how we achieve that, how we model the competition between the two geometry is by using a similar approach as this original paper, the 2013 paper. So we use the same set of parameters and solve both geometries, and then we compare the pressure. And more specifically, we compare the breakdown pressure in both geometries. So our criterion is set that whichever geometry has a lower breakdown pressure, that's the more advantageous direction for the fracture to be initiated along. So if the longitudinal gives us a lower breakdown pressure, then a longitudinal is the more favorable direction for initiation. And so is the transverse if it generates a lower breakdown pressure. So these are the governing equations. I first start with the elasticity. And in an isothermal field, we don't have this prior cooling or warm-up, so we don't have a thermal stress disturbance. But now, since we conduct a cooling circulation and the warm-up before the hydraulic fracturing, so we now have this additional term that describes the contribution of the thermal stress disturbance on the overall elastic response of the hydraulic fracture. So this term, we will call it the thermal stress term, and it can be computed by the product of the change in the temperature at a certain location, delta T, and alpha D here is the thermoelastic stress coefficient. And I remind you that this delta T is obtained by the abacus simulation. And again, since the fracturing time is much less compared to both the cooling and the warm-up, and especially because here we are only focusing on the initiation and the early time growth of a hydraulic fracture. So we can just impose this thermal stress disturbance field. It's time invariant, so it doesn't change with time. And we can directly use the temperature field that we obtained from the first model as the input here. So these are the rest of the governing equations. And as I stated, this is a coupled problem. So we have the equation that governs the fluid flow and the continuity equation. And for propagation and initiation and propagation is we impose the induced mode 1 stress intensity factor at the crack tip is the same as the fracture toughness. And finally, we have the inlet boundary condition that takes care of the compressibility at the borehole so that we can effectively model the breakdown process. So this model stems from a classical hydraulic fracturing modeling using boundary element methods. And it has been extensively validated against both analytical and numerical solutions. And I'm not getting into the details of the numerical algorithm and the methods, but if you are interested, I encourage you to check out this publication down below. And with that, I now move on to the numerical simulation results. So first, I start with the temperature field. This is for the case of a 50 degrees Celsius temperature drop. And I plot two contour plots here at 2 moments. The first is after 10 hours of cooling circulation. So it's this time here. And the second one is after another 10 hours of warm-up. So circulation has stopped for 10 hours now at this moment. And these two temperature fields are taken from this middle cross-section, as you can see in this problem geometry. And heat diffusion, it follows a linear pattern. So we can then just plot the temperature distribution with radius as shown in this figure. So here we have a few cases. So the first one is the cooling after 10 hours of cooling, so which is exactly same as this scenario. And the second is after 30 minutes after the cooling has stopped. So warm up for 30 minutes. As you can see, the temperature has already increased at the borehole and the near borehole region here. And the third case is warm up of 10 hours, which is the same as this condition. So we see the temperature distribution becomes more uniform with time after the circulation has stopped. And I also show the associated thermal stress disturbance. Here I remind you, this term appears in the elasticity equation. So for the same 50 degrees Celsius temperature drop, I plot the distribution of thermal stress on different occasions. So first, we start with the 10-minute cooling. You see, at the borehole wall, it's inducing as much as 30 MPa thermal stress. But then it dissipates relatively fast away from the borehole. So after 10 hours, it's this curve. And after 10 days, it's this case here. So we see the trend that the thermal stress disturbance propagates away from the borehole with time. And then let's look at the results during different stages of warm-up. So the first case of all three curves here, the red curves here, are taken with a prior 10-hour cooling circulation. So after 30 minutes of warm-up, we see the thermal stress has already dropped by about 1/3. And after 2 hours, it's a half. And after 10 hours, as we see the same behavior as in the temperature field, the thermal stress becomes more uniform. So these are all the values of the thermal stress disturbance. And that's, again, in the elasticity equation. But the question is by how much the breakdown pressure can be lowered. And I will show you that it is not the same as this 30 MPa. So here now I'm presenting the results in this part of the process, the hydraulic fracture initiation. And I want to start with the comparison between these two cases. The first is isothermal case, so no prior cooling and warm-up, just a hydraulic fracturing. And then the second case is after 10 hours of cooling circulation. And this is no warm-up, so hydraulic fracturing right after 10-hour cooling. And we plot the pressure evolution, the Wellbore pressure evolution for both cases. And if we compare the overall pressure evolution as well as the breakdown pressure, we see a clear decrease for the transverse geometry. The decrease is about 7 megapascal. It drops from 57 to about 50. And what's more interesting is for the longitudinal case, we see cooling completely wipes out the peak in the 10-hour cooldown case. And if we are just to take the maximum value in the pressure response and compare it with the breakdown pressure in the isothermal case, we see the drop is about 4.3 megapascal, which is much less compared to the reduction in the transverse geometry. So we believe that in the isothermal case, longitudinal is the more advantageous direction. That's because it has a lower breakdown pressure. but we see the transition from longitudinal to transverse after 10 hours of cooling. That's because now in this case, transverse becomes the more favorable direction because it has a lower breakdown pressure. So clearly the change in geometry that is induced by cooling circulation. And in fact, there is this tendency of the transitioning from longitudinal to transverse with a longer cooling duration. So here I plot the correlation between the breakdown pressure and the cooldown time. And I remind you, cooldown time is just how much time cooling circulation is carried out. So this is the case for a 100-degree Celsius temperature drop at the borehole wall, but the overall trend is the same as the 50-degree C case. So we see at first, the longitudinal is the more favorable direction because it has a lower breakdown pressure. Then with a longer cooling period, both breakdown pressures drop, but then the drop in the transverse geometry is larger compared to the longitudinal geometry. And after 2000 seconds, we see the transition from longitudinal to transverse because transverse now has a lower breakdown pressure. And we have demonstrated in these simulations that first, there is a reduction in the breakdown pressure, but it is not the same value as the induced thermal stress disturbance at the borehole wall. And second, this reduction of breakdown pressure, it is not a constant value, and it changes with time. With a longer cooling period, the reduction is more significant. And then if we take into account the waiting time, the warm-up time into consideration, now we have 2 more cases here and things get more interesting. So first, we have a case of 2-hour warm-up that's following the 10-hour cool-down circulation. And if we are to compare these 2 cases, we don't see much difference in both the pressure evolution as well as the breakdown pressure. So it's basically similar as the hydraulic fracture immediately after the 10-hour cooling. But if we wait for a longer time, after 10 hours, we now see the pressure response totally changed. So you see here in this situation, both the pressure in both geometries, they rise at the same pace, and then they peak at the same time with similar value, that is about 50.7 megapascal. And after that, the pressure in the transverse geometry drops and converges to the minimum in situ stress. That's because that's the compressive stress normal to the transverse plane. But for the longitudinal geometry, we see the pressure drops for a little while, and then it peaks again somewhere here, and then emerge with the intermediate in situ stress. That's the stress normal to the longitudinal fracture plane. So what's likely going to happen in this case is that we might see the initiation in both directions because both directions are equally advantageous, or the fracture initiation will be highly localized due to some heterogeneity or some pre-existing weak planes like a natural fracture. So we have shown with all these results that there is this overall trend of change in the geometry, and it can be only captured by the full consideration of fluid-solid coupled model in hydraulic fracturing with the existence of a significant thermal stress disturbance. And these are all based on our theoretical analysis. And now I will show you some evidence in the lab experiments. So this is the overall setup. We have a load frame and that's capable of applying confining stress in all 3 directions. And this combination of the confining stress is designed with the similar ratio as in the Forge project. And for all experiments, we use these 6-inch cubic blocks made of granite. And in the cases I show here, it will be mainly hydraulic fracturing from a vertical well. So the stress condition is that the confining stress along the borehole direction is the maximum confining stress. And for all tests, we inject fluid into the middle section of this 2-inch long of the half-inch diameter borehole, and we don't have any perforation or any notch, so we just do the open hole initiation. And the testing conditions are summarized here in this table, and I'll mainly show two series of experiments. The first is no pre-cooling test. What I mean is we heat up the sample to 200 degrees Celsius and then do the hydraulic fracture right away. So you can consider it as an isothermal test. And the second series is with pre-cooling. So we heat up the sample to the same 200 degrees C, and then we do the cooling circulation with tap water for about 15 minutes. And the measured temperature drop at the borehole wall is about 170 degrees Celsius, because the temperature at the borehole wall quickly drops to the same level as the temperature of the tap water, which is about 30 degrees C. And then after the cooling circulation, we wait for another 10 to 15 minutes. That's the warm-up period. And then we do the hydraulic fracturing test. And the injection rate is set to be constant for all tests. It's 3 milliliter per minute. And here's the combination for the confining stress. And again, we only show the cases that's hydraulic fracturing from a vertical well. So this is the vertical stress, 7.5 megapascal. And this is to intermediate and the minimum in situ stress, the horizontal stress. So here I give an example of a typical temperature evolution in the pre-cooling test. You see the initial temperature is about 200 degrees C, and it drops relatively quickly after cooling starts to the same level as the temperature of the tap water, which is about 30 degrees C. And after circulation stops, the temperature measured at the borehole wall slowly increases with time. So that's the warm-up. And these temperature measurements are taken at the borehole wall with a thermocouple. And now move on to the pressure evolution in all tests. So I start with the left figure on the left. That's the no pre-cooling test, so isothermal condition. And you see we have two breakdown pressures that are very consistent. So we have the average breakdown pressure of about 22 megapascal. And with this pre-cooling and warm-up, we do see the reduction in the breakdown pressure. But the average reduction of the breakdown pressure is only 3.4 megapascal, which is much less compared to the thermal stress disturbance. Because I remind you, in this case, we are dropping the temperature by about 170 degrees C. So this observation confirms our simulation that the drop in the breakdown pressure is less compared to the thermal stress disturbance. And now I show you some photos of the samples after test. I start with the no pre-cooling isothermal tests. So in both experiments, this is the surface of the 6-inch blocks. So in both experiments, we have only one major fracture that's both longitudinal. So here in this test, the major fracture is here. That's the direction of the borehole. And in the second test, we have, again, a longitudinal fracture. But if we do the pre-cooling and the warm-up, the geometry becomes more complex. As you can see in these two tests, we have two major fractures. So in the test on the left, we see one major fracture that's longitudinal, but then the second fracture, it's vertical to the borehole direction. That's the transverse direction. And the same as in the second test, we see one major fracture that's longitudinal, and the second one is kind of inclined. So it intersects the borehole with a certain angle. And we believe what happened there is it's actually a similar situation as we saw in the numerical simulation, that both longitudinal and the transverse, they are equally advantageous. So this initiation is highly localized due to some heterogeneity or some weak planes. So that's why we see the fracture that's inclined here. So our experimental observations show that even for the stress condition for a vertical well, so now we have the maximum confining stress, that's sigma V here. even for these stress conditions, cooling can promote transverse fracture initiation. So this is an ongoing work, and we're trying to expand our parametric study to better understand the underlying mechanism of this transition in the geometry. But at this point, we can already draw some conclusions. So first is Wellbore cooldown reduce the breakdown pressure, and both cooldown and the warm-up exert a significant impact on the initiation and the propagation of the hydraulic fracture. And we saw that cooldown promotes fracture initiation along the transverse geometry. And finally, this change in the geometry needs to be studied with fully coupled model in the presence of a significant thermal stress disturbance. And that concludes my talk today. And thank you for your attention. And we're happy to discuss with you if you have any questions.
Thank you, Guanyi. We do have some questions in the chat, and I'm not sure who they're all from. The first is from RNBY. Who is that? Just introduce yourself. Say hello to everyone. Okay. Nevertheless,
hi. Can you hear me?
Yeah.
Yeah. So this is Rajesh from Chevron.
I
just tuned in maybe a few minutes late. Yeah.
No. I just was uncertain from the.
Yeah. No. So that's our 4-letter identifier. I'm sorry. Yeah.
Okay. Yeah. Very good.
But no. Nice talk by Guanyi, and I appreciate the sharing here. Yeah. Thank you.
Well, and go ahead with your questions.
So early in the talk you mentioned, something was being circulated in this subproblem. I was just trying to understand, what process you were trying to simulate. Was it like the drilling, the cementing, and perforating?
Yes. Or? So it's not drilling, it's the kind of preparation for well stimulation, because the high temperature and can induce some damage to this device, especially the electronic device for monitoring and for well stimulation. So this is the step prior to the well stimulation. So we just circulate, as I showed this example here at Forge, circulate a cold fluid in the wellbore, and the fluid pressure is relatively small, so we neglect, and I guess that's the second problem you ask here. Abacus has a poro-thermoelastic element. We don't use that because we neglect the pore pressure diffusion during the circulation. That's because again, two reasons. Actually, I think I have a slide and can show you here. So we have negligible circulation pressure, as I explained, and also the heat diffusion, it can induce some pore pressure. But then we can compute it based on some semi-analytical solutions. So here I showed these two cases of the pore pressure distribution after the 1-hour circulation and 10-hour circulation. So you see the values, they are relatively small. So they are less than 1 megapascal, and compared to the tens of megapascal of in-situ stress and fluid pressure, and it's negligible. So we neglect both pore pressures, and so basically we just take the temperature field and we use the heat diffusion element type to model that part in the Abacus.
Right. Okay, so I'm assuming like the rock you're looking at is like quite a stiff rock.
Yes, it's well.
Okay, so the rock skeleton is pretty stiff, I would assume. So that's why the induced change in the pore pressure is small.
Yeah, we use all parameters, the thermo-poro-mechanical parameters of granitic rock, and so this is
it's a volcanic. Okay, understandable. Yeah. Okay.
Thank you. Were there any other questions? Igor. Igor, why don't you just articulate your question?
Sure, sure. Okay, thank you. I mean, as I said, I mean, it's excellent talk. I really enjoyed it.
Thanks.
So my line of thinking is essentially how to bring it to the field scale, right? And so what would be the potential challenges, and complications? Because uh, the way it looks like is that you can change. I mean, you could cool down the wellbore, and now you can avoid having near wellbore complexity by initiating transfers, initiating in the
Yes.
right direction, right? And so it would be nice to have a field experiment, one way or another to validate this because neural complexity can be measured in the step down tests, and so you have, several step down tests, with cooling, without cooling, you can see clear change. This could be a confirmation that it all works. But at the same time, and another thing that bothers me in this is cement integrity, right? So what if you do this extensive cooling and now this crushes your cement, right? Introduces some cracks or damage to your cement. Will it make things worse or not? And again, and this is something, I mean, maybe you cannot answer, you need to do some more research, but something to keep in mind at least.
Yeah, that's a very good suggestion. And actually, we are working on the first question that you have, the kind of field test, because we have the data of the mini frag tests that's conducted after this cooling circulation. So we already have the data, and we are looking into the data, trying to interpret the pressure response we got from these mini frag tests and see if we already see that cooling can change the overall pressure response. But then in terms of the change of geometry, it's more complicated, right? In my view, it's a combination of several factors: the stress state, the propagation regime that we are looking at, and also the kind of microscopic structure of the rock. Because we do see some evidence in the lab that cooling circulation can induce thermal cracks, and sometimes they can be transverse, and sometimes they can be longitudinal. I guess this is also related to your second question, is about the near wellbore complexity. And so it's at this point we are investigating into this kind of both modeling in a continuum level as well as the lab experiments in a microscopic structure. But yeah, that would be interesting if we can expand our parametric study and to compare it with the field data we collected in the mini frag tests.
Okay, excellent. Thank you.
And Gongli has a question on the capabilities of loading capabilities in the laboratory, and I see Yunxing has posted an answer to that. Maybe you want to elaborate on that, Yunxing.
I'm sorry, this is Gangli. I want to clarify what I mean by that. First, of course,
sure.
yeah, thank you very much for this fantastic talk, especially the lab testing results. I'm very interesting to see that. I guess my intention of this question is try to understand how you actually load the specimen, and is that by stress control or strain control? What do you consider your loading condition compared with the real field boundary condition?
Yes, so it's controlled by pistons that's pressurized. So it's stress control. The confining stress are applied, and the combination of the confining stress is designed with similar ratio as in Forge. So we have kind of a normal stress regime. And I would say that's the typical way to do hydraulic fracturing in lab scale. And so we use the fixed confining stress instead of fixed displacement or other loading conditions. So it's
I guess. Thank you very much. I guess what I had in mind is like I want to hear your comments. Like normally, right, when we think about field conditions, I'm not sure about overburden. We probably can use stress control, which simulate the field better, the overburden. But for the horizontal stresses, we often consider uniaxial load, right? Basically, the boundaries, like you apply the stress, but then you keep the strain constant, and let the stress play, right? But in your case, if you are applying active stress on both sides loads, do you think that can be different than the field?
If there's no like a thermal effect, it will be identical to the field, in my opinion, in the field case. But then if we do have this circulation and warm up, so what we did is that we load the sample first and then do the cooling circulation with this confining stress. And during the same time, we are, I think, Yunxing, you can correct me if I'm wrong, but we are still applying the same stress, so we don't change the confining stress during cooling circulation.
Yeah, what I was referring to is that if you keep the stress, the boundaries, like the side stress especially, you apply the stress to the level you want, and then you lock it up, lock the strain up. And then like,
oh no, we didn't. We just fixed the
but
confining
if
stress.
you do that, and then you cool the stress down, you cool the specimen down, I'm assuming you probably have a different result, right? Because you have the rocks relaxing. And I was just wondering, which way do you think gonna mimic the real field better?
A better way is to have a larger sample, right? But then, and I think the method we are applying, it's closer to the in situ condition. We're just applying a constant confining stress. Cooling, if we do a longer duration, like hours, then it will definitely affect the stress away from the borehole. But since we are only using 15 minutes to cool down the specimen, so according to the results, that the cooling circulation and the thermal stress disturbance is still concentrated near the borehole. So in the far field, it's still, you can consider it as the isothermal, or the temperature doesn't change at the boundary, and we are still applying the same confining stress.
Thank you so much, sir. Thank you. Appreciate it.
Thank you.
Good question. If we have time, we can come back to that. Obena he has a following up on the practical questions, and I apologize if I've mispronounced your name. So does this imply that in a multi-stage hydraulic fracturing treatment, subsequent frac stages are more likely to experience lower breakdown pressures, as well as fracs propagating transversely rather than longitudinally?
I'm sorry, I'm still reading this question.
Okay.
So
maybe if you can read it.
Sure. Multi-stage treatment.
So in a multi-stage, you presume there's going to be more cool down with time.
Yes, that is true. But then in a multi-stage fracture treatment, and you need to consider the stress shadow. Right? So I cannot say intuitively, whether the breakdown pressure will be lower or it will be affected by how much. But in our analysis, first, you need to keep in mind that the circulation lasts for hours, right? Even like days in the case of forge. So this is a significant amount of time. And so the thermal stress is larger in this case if we do the prior cooling circulation. And in the fracture, in the well stimulation, I don't think the thermal effect will be this much, but it depends on the temperature as well. So if you are a larger temperature difference, then the thermal stress will be, of course, bigger.
Cool. And then there is a question, was thermal insulation used between the preheated block and the loading frame plate?
I don't think we use any insulation, but according to the measurements, the temperature, we heat it up in the oven and then take it out and do the experiments. So the time between these two steps is relatively short, and we don't see the temperature drop that much by our measurements.
Excellent.
I think Yunxing had a clarification further down too, which is that the platins are also preheated. So you're not
yes,
getting,
right. Yeah. I forgot that. Yeah.
that's kind of an
Yes.
important part.
Thank you, Andy.
Yes. Yes. So
And-
the platins we use to apply confining stress, they are also heated to 200 degrees C. So we are kind of isolating the sample with a surrounding platins.
Yeah, sorry, can I jump on this point? So because Guanyi, you are showing these slides on the second figure, so all the loading plates here were heating to the same temperature as the testing temperature as block.
Yeah.
So we're trying to
These
use
plates.
this method to reduce the thermal loss during the test.
Excellent. And gallium. Gallium, do you want to pose your question? Maybe not. He's Gallium's just wondering how close things match theoretical or anticipated classic breakdown behavior.
Sorry, which question?
This is from
Is it
gallium.
from gallium?
Yes.
I see he's asking where are your heating elements in the loading plates? Did you achieve?
Excuse me, I could not connect very John, hello, Guanyi.
Hi. Okay, it's
Hi, Gallium.
better than me trying to do it.
Yeah. Thank you so much. I'm really sorry I have trouble to connect. A very interesting presentation. Thanks a lot. I was myself looking at this problem for some time, and really I'm glad that you advanced so far away actually in this direction. My question was in the beginning of your presentation, Guanyi, you shown basically the Heimson formula for breakdown pressure corrected with this thermoelastic stress component, right? This beta delta T. So I'm sorry, maybe you already emphasized it in your presentation, but from your experience and modeling, that sophisticated modeling, how good is this formula basically? This was my question here. Can it be used for simple estimations? Because this formula is very simple, right? But how good it is from your basically.
Yes. Yeah, I see. So if you have a fluid-driven fracture, then I would suggest this expression is not accurate, very accurate. But if you are, having something that's, a pressurized borehole and there's no fracture initiation and propagation, then this can be accurate analysis. So what I mean is that because we know fractures, and many studies have shown that the breakdown pressure in hydraulic fracturing, it doesn't happen at the initiation point, right? So it happens after the fracture starts to grow. So after fracture starts to grow, the Wellbore pressure still increases with time, especially for the case that's a viscosity dominated region.
Yes.
So there's this competition between length scales, right? The length scale of heat diffusion and the length scale of the fracture when it reached its peak value. So if the fracture, when the fracture reached its peak value, the breakdown pressure, if it already outgrows the heat diffusion area, then the breakdown pressure can be high. But if it stays inside the length scale of the heat diffusion, then that's likely this scenario that we see in the longitudinal case. So you don't see that much peak. You don't see the peak is somewhere here, and it's kind of wiped out, and the fracture has already grown in this period, the longitudinal fracture.
Okay, I see what you mean. Of course, yes, there is no even injection parameters in this formula, and yes, stuff like that. But basically, that formula assumes that you release stress concentration near the created by Kirsch. You release it, you reduce it actually by stress, thermal stress. This is what basically that formula assumes. Yeah. Okay, Guanyi, thanks a lot, really, indeed. Yes.
And then there's another. Oh, sorry. So there's another question about whether or not your
Sure.
model could handle propagation along weak bedding planes.
Well, it's a 1D geometry. So right now it's only a preset path for the fracture growth. So as I show in this geometry, so the longitudinal is set to be normal to the, if we are looking at the horizontal well, then normal to the intermediate in-situ stress. And the transverse is normal to the minimum in-situ stress direction. So it's a kind of 1D direction.
So Guanyi, that is my question. So this is Rajesh again from Chevron. So I was wondering, I got the impression your model could handle like both mode 1 and as well as the other modes of fracturing. So
just mode 1 open.
Just mode 1. Okay.
Opening fracture.
Okay.
Yeah.
Okay. Thank you.
Thanks, Rajesh. Andy had a comment. Andy Bunger. Do you want to elaborate, Andy?
Well, Guanyi covered it completely. I was just responding in the chat to what I saw there. So I don't really have anything to add to what Guanyi already said.
Okay. Luke. What, can you just unmute yourself and pose your question or your comment? Oh no, Mike, I forgot. Okay. So this is a long one, Guanyi, so maybe we both better read it together. Okay. So actually it's a good practical question. You know, what changes in field practices would there be in order to use the cooling effect that are different from what is already done? He notes that strong temperature drawdown will damage the well and the cement if done too quickly, and that a cooling effect is already likely to occur during normal stimulation operations. And then the observation is perhaps this helps us understand breakdown pressure more accurately.
Yes, that's one of the goals, is to help interpreting the pressure response measured from the mini-frac tests. So to help interpreting the in-situ stress. And then I would say the difference, well, first of all, we have an open hole section. So no cementing and no perforation. And so that, in fact, that effect, I cannot say for sure how it's going to impact this cooling effect coupled with cooling effect. But the part you mentioned, that's cooling effect already likely to occur during normal stimulation operations. Yes, but then I want to reiterate that the cooling circulation that's carried out prior to hydraulic fracturing stimulation, it's a very long time and also a larger amount of fluid, and they circulate the fluid and with some chiller, and so this temperature effect is more significant compared to you just inject fluid into downhole, because during this time the fluid will be heated up, right? And if you consider the little amount of fluid that's being used during fracture initiation, so here I'm only talking about early stage, so little amount of fluid, then the temperature in the fluid will likely be very consistent with the rock temperature. So there will be less difference in temperature and less amount of time in cooling. So this prior cooling stage will exert more significant impact in terms of the thermo-mechanical effect on the fracture initiation.
Thank you. Well, Guanyi and Yunxing, you've certainly generated a lot of interest, and this is fantastic work. You really need to be congratulated on it, and it's important work too. So thank you so much for your presentation.
Thank you all for coming.
Thanks everyone for attending.
Yeah, thank you.